Greetings and welcome. In today's video, we're going to be talking about graphing and solving quadratic inequalities. So this is going to merge two previously learned skills, which is graphing quadratics or parabolas, and graphing inequalities, in which we have to know whether or not to shade above or below a graph, and whether or not the line of the graph is solid or dotted. So I've got the equation. Y is less than or equal to negative 2x squared minus 16x plus 4. And I can technically graph this by making a table of values, by finding the vertex, the roots, and the y-intercept. I could also put it in vertex form. And since we just did some vertex form problems, I figured let's practice that skill a little bit further. So what I'm going to do first is factor out the a from the first two terms, which is negative 2. So I'll have y is less than or equal to negative 2x squared plus 8x blank plus 4 blank. All right. Notice that negative 2 times positive 8x is in fact negative 16x, so it does work out. And now I'm going to find my new c term. So c is going to equal 8 divided by 2 all squared, which is 4 squared or 16. So I'm adding 16 in the world of the parentheses. Now in the world of the problem, I was really subtracting 32. So in order to balance that out, since I'm operating all on the right-hand side of the relationship, or the less than or equal to sign, I'm going to have to do the opposite of it over here. So I was subtracting 32, so over here I'm going to add 32. So let's fast factor this. So y is less than or equal to negative 2 parentheses what all squared plus, looks like 36 on the outside here. And this fast factors to be x plus 4 all squared. One of the ways you can find this positive 4 is it's the number we had right before we squared it when I was finding my new c term. So the information I can gather from this is a is equal to negative 2. My vertex is at negative 4, comma 36. So let's graph this. So let's see. It opens down because the a value is negative. The vertex is over 4 up 36. So it looks like it primarily is taking place in the second quadrant. And let's see. I might have to count by sixes here. 6. That might not even give me space. So 6, 12, 18, 24, 30, and 36. And I knew I wasn't going to go any higher than 36 since my graph was opening down from my vertex. And then here I'll count normal 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The ugly 10 there. 2, 3, 4, 5. So, and then let's see, I'll even go down to negative 6. So let's graph our parabola. So I've got negative 4 right here, and positive 36 is my vertex. And now the parabola opens down, and it's been stretched by a factor of 2. So I guess I could do some a little additional work regarding my slopes. Right, my quote-unquote slopes, as I call them. So normally it'd be 1 over 1, 3 over 1, and 5 over 1. And I would have to multiply each of these numerators by my a value, my negative 2. And specifically the numerators, even if this was just a fraction, if this was a fraction for my a value, it would still be multiplying just the numerator by that fraction. So it could get a little bit ugly, but it works out. So I'll go down 2 over 1, down 6 over 1, and down 10 over 1. So for this, I'll go down 2 over 1. So that would bring me down to 30, a height of 34, and I'm at negative 3 here. Then from 34, I'll go down 6, so that would bring me down to about 28, or exactly 28 technically, and over 1. So here's the point, negative 2, 28. And then I'd go down 10, which is going to bring me to 18 over 1. So here's the point, negative 1 comma 18. Now actually, I think because this was in standard form originally, I actually also have my y-intercept here is at positive 4. Let's just verify that this would work. The next slope, quote-unquote, would have been 7 over 1, and multiplying that by negative 2, I'd be down 14 over 1, and that does in fact line up with that right there. And I can also use my axis of symmetry to find some additional points on my graph. So this is 1 unit away, so 1 unit away here, 2 units away, so 2 units away, 3 units away, so 3 units away, 4 units away, so 4 units away, right there. Now, regarding my parabola, check this. Now, let's analyze what this symbol says here. So, because of this tells me a couple things. Less than or equal, the equal part tells me that it is a solid curve. The less than part tells me that it's shaded below. Okay? So when I graph this, I guess I'll graph in green, it's going to be a solid parabola. It's possible I would have had a dotted line parabola, just so you know. Okay? And something like that, I imagine. I don't think it crosses at negative 10. I think it crosses before that. And then the points that are less than this parabola are the ones underneath it. Okay? Now I want you to avoid the temptation to think of inside and outside the parabola when it comes to shading, because if this parabola was pointing up and I was thinking of the points less than it, it would be the points still below it. Alright, so think above or below as far as shading goes. So my solutions are all of the points in this shaded region. Right? And like I said, if this was just strictly a less than symbol and didn't have the equal part, then it would have been a dotted parabola, and all of the solutions would have been the shaded region there. Now, what I can do is pick a point in the shaded region to verify that it works. In this case, the easiest point I have is the origin, 0, 0. So just as a check, let's see, what was the original equation? Y is less than or equal. Maybe I can grab a snapshot even. See how clever I am. There we are. Man. So I'm going to try the point 0, 0. Technically, any point within the shaded region should work, but 0, 0 is usually a really friendly one. Is 0 less than or equal to negative 2, parentheses 0 squared, minus 16 times 0 plus 4. So is 0 less than or equal? 0 squared is 0, times negative 2 is 0. So that's 0. Negative 16 times 0 is 0, minus 0, plus 4. Is 0 less than or equal to 4? And yes, I believe that is a true statement, right? And I could, even if I wanted, pick a point outside the shaded region and verify that that doesn't work, indicating that we are, in fact, correct. So, so there's kind of an interesting type of problem, the way you can graph that parabola. Let me give you another situation here. Let's see, I think I'll be able to fit it here. What if I have a rectangular box that has W centimeters for the width and W plus 6 centimeters for the length. Alright, so these are in centimeters. And so the rectangle is 6 centimeters longer than it is wide. Find the possible dimensions if the area of the rectangle, so what if I told you that the area is more than 216 centimeters squared. Alright, so this is a little bit tricky. We've got way more variables than we're used to. But think about this. This is a rectangle, and what is the area of a rectangle formula? Area is equal to length times width. So I'm going to just plug in what I know and then eventually solve for what I don't. So I have that the area is greater than 216. So this area is 216, and whatever I calculate the area to be has to be bigger than that. And what's the area? It's going to be the length times the width. I'm actually going to write the width times the length. It's the same difference. I think you guys would agree. W times W plus 6 is the area, and the area, as I said earlier, has to be bigger than 216. So now I've got this equation here, and I'm interested in solving it. So what I'm going to do is distribute. I can't set both of these equal to 216, by the way, because the zero product property does not apply when it's not equal to 0. So let's see, w squared plus 6w is minus 216, I guess, is greater than or equal to 0. So this is what I'm interested in, right? I could get that when I subtracted 216 from both sides. I want to know when are the values of w bigger than 0 for this equation. And those will be solutions of the problem, and those will give me rectangles that have areas bigger than 216, right? So one of the ways I could do this is I could actually graph the parabola, all right? So I could translate this into a function, a quadratic function, and take it from an equation, or inequality, I guess in this case. And I want to figure out when is this going to be less than this equation. Okay? And if I graph this and take my y values, figure out which y values are less than this, that will give me my solutions. So let's graph this. So this is a regularly shaped parabola that's opening upwards, and I'm going to graph by putting it in the what form is it? Vertex form. So that will be w squared plus 6w blank minus 216 blank. Find my new C term. I'm going to cruise through this with very little explanation because we've seen it before. So 3 squared equals 9. Adding 9 in the world of parentheses was really adding 9 in the world of the problem. So to balance the world out, I have to subtract 9 over here. And I would have f of x is less than, fast factor this, w plus 3 all squared minus, what's that going to be, 225, is it? Right? Something like that. So I could then graph this. I wonder if I can open up my graphing software. I think I will. So while that is starting up, I think I've got a whole bunch of different windows that'll auto-open on it. But so I can graph this. The reason I'm opening it is just because this number is going to be quite a ways off the chart, so to speak. So let's see. Let me open up a new window here. And I'm going to graph a function. Now, in the case of this software, it kind of only it'll graph the equality of it. I can tinker around so it will handle and give me a shaded region, but I'm interested just on where this parabola is. So my w is x. My function is still f of x here. Actually, I guess this should have been f of w here technically, shouldn't it? And let's see what my graph looks like. That's not very helpful, but let's zoom out. Like I said, the vertex I knew was going to be at negative 216. Let me change this so that it's not rectangle or a square grid. Actually, yeah, I think I'll something like that. And actually, I'm going to delete this for a minute and regraph it so it draws the full parabola. So, so this is what I end up getting. Let's see, I can hide those points because I don't need those. And this is what we've got. Actually, can I get greater variation there? Good, beautiful. Thing of beauty. I'm even going to grab a snapshot of this right here. And go back to this. So I paste this, and voila, I've got myself a very pretty graph. So for this equation, I was interested in the values of the function that were less than this parabola. So what values are less than the parabola? Well, that would have been everything underneath it, right? So all of these points here, all of these points here, right? And actually my parabola itself would have been dotted. I don't think you guys can see that well. Right? So I would have had a dotted parabola and everything beneath it would be solutions. But now I didn't originally have a function. I had just an equation, and I wanted to look at the relationship specifically when this equation was related to 0. So notice that I replaced 0 with my y, or my f of x. I'm going to boil this graph down to just one dimension, where I'm going to now take all of my y values, and let's just think about where this graph exists on the x-axis. So let's ignore all of the y's. And it's been a little while since we've graphed on number lines, but let's look at what our graph looks like on just the x-axis. So here is 0, here is 10, I think then it looks like I've got -10, -20. And if I look at just the solutions here, it looks like at 18, it's not equal to 18, right, because it's dotted there, but at 18 would be an open circle and it's shaded to the left. And it looks like at 12, it would be an open circle and shaded to the right. So would you guys agree that this represents the solutions on just the x-axis, the values for when my function is equal to 0, right? So all of my solutions on the x-axis can be boiled down to this number line. And what does that look like? Well, let's write an equation or inequality, compound inequality, that represents that. Now they're shaded away from one another, so it's an OR problem. And I have w is less than 18, or w is greater than 12. So graphically, that's a way that I was actually able to solve this problem, where I was actually only interested in the behavior on the x-axis here, but I was able to use that to give me the solutions to the equation. All right. So if I want actually, oh, sorry, that's -18. My bad. Silly me. So now, to bring this back into the context of this rectangle, w could be less than -18. Okay, a width of -18 doesn't really make sense in the real world. So I'm going to exclude those solutions, right? Or w is greater than 12. And let's just do a quick check. Let's check like 13, all right? Let's say w equals 13. So if w equals 13, is my area in fact going to be bigger than 216 square centimeters? So let's see, so if w is 13, what's the length? 13 plus 6, that gives me 19. So is 13 times 13 plus 6, is that bigger than 216? So is 13 times 19 bigger than 216? Let's see. 13 times 19 is 247, which is bigger, sorry about my less than signs looking like 7s, is bigger than 216. And any value of w bigger than that, 12 would work. Now what happens if I try 12 exactly? Well, that would have been 12 plus 6 is 18, so 12 times 18 is 216 exactly. So that would actually have landed right on, right here, right on the line, but I'm not interested in that because I wanted it specifically to have an area greater than 216 centimeters squared, not greater than or equal. So that's kind of, this is a little bit more of an abstract problem, but I think it's worth pointing out. It has some interesting behaviors to it. Now it turns out we can't actually solve these quadratics without graphing. I could have solved this using some different techniques, somewhat of a zero product property. And I'll do one last example just to show us how to do that. Oh man, I am already at 20 minutes, but let me do one more example. What if I want to solve the following? X squared minus x minus 12 is greater than 0. So what I'm going to do here is I'm actually going to factor this. It's equal to 0, so that's why factoring could be helpful. So what are the factors of 12? Let's see. 1 and 12, 2 and 6, 3 and 4. Which of these subtract to be the b, the 1? 3 and 4. So I'll have an x with a 3, an x with a 4, greater than 0. And let's see, they multiply to be negative, so their signs are different. And they add to be negative, so the more influential number must have been negative. And now, this is kind of interesting. I don't quite have the zero product property, but I have two numbers that I know multiply to be something bigger than 0, or two numbers that multiply to be a positive. All right? So I guess I could describe it this way. Two numbers that mult to be positive. So I can actually break this down into two separate cases. Either this one's positive and this one's positive, right? It could be plus plus, right? Actually, I'll call this case 1. Case 1, positive, positive. And then case 2 will be negative times a negative, right? Because negative times a negative is also positive. So these are the two cases that I have to consider. So either x plus 3 is greater than 0 and x minus 4 is greater than 0, or this case over here is true, in which x plus 3 is less than 0 and x minus 4 is less than 0. So let's solve all of these and see what happens. So x greater than negative 3 and x is greater than 4. So let me represent this on a number line. So here's 0, here's negative 3, here's 4. Graphing this, I would have greater than negative 3 would be an open circle shaded to the right, and x is greater than 4 would be an open circle shaded to the right. Now it turns out this does have some overlap. The overlap occurs at the 4 and on, right? So I could actually boil this down to being just x greater than 4, all right? Because this is redundant to say x is bigger than negative 3 and x is bigger than negative 4. X is bigger than negative 4 actually kind of covers all of those cases, right? Because this is the situation where both were true. That's what and is implying. Both of these had to be true, okay? So now let's solve over here. This would have been x is less than negative 3. And this one would be x is less than 4. So when I graph the number line over here, I've got 0, I've got 4. Man, my 4s are always showing up terrible lately. And negative 3. And x is less than negative 3, open circle shaded to the left. X is less than 4, open circle shaded to the left. The only points in which both of these are true are the ones in which x is less than negative 3. Okay? And now because it was either of these cases that were true, there was kind of an or between them. This is kind of a really abstract problem. But it's this or that are true. So my actual solution is x is less than -3 or x is greater than 4. And if I wanted to represent that on a number line, I would have had 0, I would have had 4, I would have had -3, and x is less than -3 would be this one, x is greater than 4 would be this one. And these would be the solutions of this quadratic inequality. And to verify, I could actually even pick a point from each of these locations to try it. So if I was to do a check, I would have to check the points, say I'd try -4, something in the shaded region. I would probably try 0, something between these two. I would expect 0 not to work. I might even write 0 in red just to indicate that. And I would try something like 5, something in that shaded region. And all of those should work. X squared minus x minus 12 was the original equation. Greater than 0. Let's just do a quick check. Is -4 squared minus -4 minus 12, is that, was it greater than? Yes, 0. Yeah. So -4 squared is 16. Minus a -4 is +4. Minus 12 greater than 0. 20 minus 12 is 8, which is greater than 0. So that's true. So that means this is true. Let's try 0, which we're expecting to fail. All right. Is 0 squared minus 0 minus 12, is that greater than 0? 0 minus 12 is -12. Is -12 less than 0? No. So that one failed intentionally, which is what we were looking for. And lastly, let's try 5, the last shaded region. 5 squared minus 5 minus 12, is that greater than 0? 25 minus 5 minus 12 greater than 0. I believe that's 13, which is greater than 0. So that does in fact work out. So it appears as though I do have the correct solution, which is this right here. Let me box that a little bit better. So, so this is a way that it can be done using case logic. You can solve that. Or, I mean, like I showed you in the previous example, I could have graphed the equation y is less than x squared minus x minus 12, and then looked specifically at the x-axis of the shaded region and boiled it down to that, and I would have gotten the same solutions. All right, so I hope that is helpful. That is solving quadratic inequalities, and I will see you guys